a set of axioms and inference rule, and any structure that you can form using the symbols, in the system, and the bigger structure formation rules, they should be provable as a theorem or not. Okay. Now we introduce now semantics in the framework. We have something called a valuation function. So the valuation function is defined as follows. Valuation of f is Roman f. Okay, valuation of Gothic f is Roman f. So you must understand the difference between Gothic f and Roman f. So Gothic f is a symbol of the formal system. Okay, and Roman f is the value of that Gothic f symbol. So one is in the syntactic world, the other is in the semantic world. Okay, so Gothic f is in the syntactic world, Roman f is in the semantic world. So f is called false and is one of the two symbols T and F. So V of Gothic f is Roman f. Another part of the definition is valuation of A implies B is given by this table, which is also called the truth table. So in the truth table, we see that valuation of A implies B is false only when valuation of A is true, valuation of B is false. Otherwise, it is always true. Okay, so this is how the valuation function is defined. Now, this valuation function is the bridge between the syntactic world and the semantic world. So if you are thinking about why this nitty-gritty and nitpicking about valuation function, syntax, and semantics, we can better understand this from what is called the language world. Okay, and we have already seen that for some of the statements in the language world, the truth value cannot be determined. Okay, for example, the sentence, this sentence is false. The truth value of this sentence cannot be determined. Sun rises in the east, grass is blue. Okay, so the truth and falsity of those sentences can be determined. Okay, do also reflect carefully about when did the truth of these sentences emerge. Okay, why do we say that sun rises in the east is true and grass is blue is false? Okay, when did that happen? So this requires introduction of a world where all these words obtain their meaning from, and truth and falsity are determined with respect to that word. Maybe there is some planet where grass is blue. Okay, so there grass is blue. This sentence will be true. So truth and falsity depends on the world in which we operate. So tautology plays a very important role in semantics. So if an expression is such that its value is always true, okay, whatever with the model means give any value to the propositions, the value comes out to be true. So for example, F implies P, Gothic F implies P. This we have already seen. This is a theorem in Hilbert's propositional calculus. F implies P. And this is a powerful observation because this says that if the formal system can prove F, then it can prove anything. Okay, so this becomes the system becomes vacuous. So there are two models for this formula. Gothic F implies P. VP is true and VF is F. There are two models. And in both cases, the value of Gothic F implies P is true. Okay. So this you can easily see. Since the valuation of the left-hand side is always false, any implication formula where the left-hand side is false, the formula necessarily has to be true. So this is an important point. Gothic F implies P is provable as a theorem in the formal system. And this theorem also happens to be a tautology. So this refers to the soundness of the formal system. Anything that is a theorem, anything that is provable as a theorem, its semantics also should be true. That means it should come out to be a tautology. So that is the meaning of soundness. And the opposite, if the opposite is also true, that anything that is a tautology is also a theorem, then we say that the formal system is complete. Okay, so completeness refers to the power and soundness refers to the correctness. So Gothic F implies P is a theorem. Gothic F implies P is a tautology. Theorem to tautology is soundness. Tautology to theorem is completeness. Okay. So if a system is sound and complete, it does not matter how you prove or show the validity. So if a system is sound and complete, then you can take any structure and either show that it is a theorem, then it has to be a tautology also. Or you can show that the structure is a tautology, then it has to be provable in the system. It will be proved as a theorem in the system. So I can take either the syntactic path or the semantic path. So syntax versus semantics really refers to the age-old philosophical dichotomy of form versus content. So this cup, which is in front of us, it has a form. And the content of the cup is tea. Okay. So the valuation of a formula is the content, and the structure of the formula is a form. So there is a very celebrated book called Gödel, Escher, and Bach. Gödel, Escher, and Bach, which is really a very nice treatise on foundations of AI. Okay, so this is called Gödel, Escher, and Bach. These three names refer to Gödel, logician, Escher, painter, and Bach, musician. So what connects all the three together is the way they use self-reference. Okay, so Gödel uses self-reference to prove that any powerful logical system is necessarily unsound. Okay, completeness and soundness do not go together for a powerful system. Escher makes use of self-reference to create paintings, okay, which do not seem to make sense, because there are descending and ascending stairs, for example, one of the celebrated paintings of Escher, where if we keep on rising on the stairs, ascending the stairs, you seem to be rising all the while. Okay, after a time it should descend, right? That doesn't happen. I'll try to show some pictures of Escher in the next class. And Bach is a musician. There, Bach uses self-reference again extremely ingeniously to create structures where you think that the musical notes are always ascending and they're never descending, but it's still a piece of music. Okay, so all of them make use of self-reference, which is really a very, very important point about any AI system. This book is by D. Hofstadter, who is a philosopher of artificial intelligence. Now, suppose we had to prove that P and Q implies P or Q. This is true, right? The sky is blue and the grass is green implies the sky is blue or the glass is green. So P and Q is a stronger condition than P or Q. So to prove that this is a tautology, we can create the truth table of this. And you can see that these 4 models, which come from taking 4 values of P and Q as a combination, true F, true, true, false, 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 true. And P and Q gives me false, true, false, false. P or Q gives me true, true, false, false. And finally, the formula is shown to be valid in all the models. So it's a tautology. So this path is very easy. Okay, showing tautology is a very easy proposition because of the truth table. Syntactic path is not easy. It is non-trivial. It requires some clever use of axioms and inference rules. But deduction theorem comes into our aid. P and Q is written as P and Q is written as P implies Q implies F implies F. This is by definition of AND, where AND is a shorthand. And P or Q is written as P implies F implies Q. So now, if you apply a deduction theorem, you can take material on the left-hand side of the derivation symbol and try to prove it. For example, you can say P implies Q implies F implies F, and P implies F derives Q. If that can be shown, okay, by deduction theorem, then our job is done. So this is what we do. P implies Q implies F implies F, and P implies F and Q implies Q. Instead of that, there is a nice trick which is almost always used. Q from the right hand side is converted to Q implies F implies F, and Q implies F is brought to the left hand side. This is because of the axiom 3, A3. Okay, so showing that this structure and P implies F derives Q is equivalent to showing that this structure P implies F, Q implies F finally derives F. Because deriving the F symbol is a very definite path. Okay, so that's a much more convenient thing to do. So does this left-hand side derive the right-hand side, namely F? So it requires a little bit of work. So Q implies, what it is saying is that from these 3 things as hypothesis, show that the last line is F. Okay. So Q implies F is given as a hypothesis. This is given. And Q implies F implies P implies Q implies F is an axiom. We apply axiom 1, instantiating B to P and A to Q implies F. Okay, so this is the hypothesis. This is a hypothesis and this is an axiom. Now, if I apply modus ponens, then we get P implies Q implies F. So, so we get also Q implies F is a hypothesis. Okay, and Q implies F implies P implies Q implies F is axiom 1. So from these 2, I derived P implies Q implies F. This is modus ponens. Okay, and then these things derive F. These things derive F because I have P implies F and Q implies F, which is also there on the left hand side. Okay, so so from these 2, if applying modus ponens again, I finally get F, which is the thing to be proved. So the syntactic path is more laborious. Okay, Syntactic path is more laborious. In tautology proving, we just have to set up the truth table. Of course, the memory requirement is 2 to the power n, right? Where n is the number of variables in the proposition. So the storage requirement is exponential. The storage requirement is not exponential in syntactic method, but the processing may take time. But I doubt if any formula requires exponential time to be proved. Okay, but the tautology path requires exponential storage. Okay, so now the proof of deduction theorem, the proof that Hilbert's axiomatic system is sound and complete. Those are very nice proofs. Okay, but we'll for the moment shelve those things and come back to them later. But move to something which is needed more in AI, in artificial intelligence, because AI is concerned with knowledge representation. How do we represent the world's knowledge and put it in computer so that it can do some meaningful operation? So I introduced predicate calculus through what is called Himalayan Club Example. It is originally called Alpine Club Example from a very celebrated book on theory of computation by a theoretical computer scientist, Zohar Manna, 1974 book. So the problem is as follows. This is a form given in the form of a puzzle. A, B, and C belong to the Himalayan Club. Every member in the club is either a mountain climber or a skier or both. A likes whatever B dislikes and dislikes whatever B likes. A likes rain and snow. No mountain climber likes rain. Every skier likes snow. Is there a member who is a mountain climber and not a skier? Out of this ABC, is there anybody who is a mountain climber and not a skier? So this is like a standard puzzle which you often meet. Now, what is the answer? Is there somebody? Anybody? Okay, so let me try to reason it out. So A likes rain. So that means B cannot like rain. A likes snow, so B cannot like snow. Now, every skier likes snow. If anybody is a skier, he or she must like snow. Since B does not like snow, B cannot be a skier. But in the club, every member is either a mountain climber or a skier or both. If B is not a skier, B must be a mountain climber. So the answer to this puzzle is that B is the required person. Okay, I think this hardly took you any time to figure out, just from the knowledge that is given in the puzzle. Okay, so now let's see how predicate calculus will be used to solve this puzzle. We would like to first understand the two basic types of knowledge. The first type of knowledge is called fact. The second type of knowledge is called rule. Okay. So the facts and rules which are given are as follows. So we have started doing predicate calculus. We have to introduce symbols for our representation. Let MC denote mountain climber and SK denote a skier. Knowledge representation in the given problem is as follows. Member A is a member of the club. Member B, member C. Notice how a natural language sentence is converted into 3 predicate calculus expressions. So here comes a suggestion for your lab project. You might think of creating a tool which takes natural language sentences and converts them into predicate calculus expressions. Okay, so this is called language to logic mapping. You might want to think of this as a project. So A, B, and C are the members of the club. One sentence gives rise to 3 predicates: member A, member B, member C. Next piece of knowledge that we have is every member of the club is either a mountain climber or a skier or both. So this is represented by the following structure. This inverted A is called for all. So for all X, member X implies mountain climber X or skier X. Notice that we have to make use of this inclusive or, not exclusive or, either a mountain climber or a skier or both. Okay, so for all X, member X implies mountain climber X or skier X. The brackets are important here. Then every mountain climber, no mountain climber X rain. So for all X, mountain climber X implies not like X rain. Okay, then every skier likes snow. For all X, skier X, SKX implies like X snow. Okay, this is the second, third rule. Then we have another rule. If B likes something, A doesn't like it. Or whatever A likes, A does not like anything that B likes. This is represented as for all X, like BX implies not like AX. And the opposite is also true. For all X, not like BX implies like AX. We are told that A likes rain, so like A rain. A also likes snow, so like A snow. Now the question is converted to a predicate calculus form. Does there exist a member who is a mountain climber and not skier? So see how it is represented. Okay, this is called, this is actually proved by contradiction. You assert that there exists an X who is a member X and symbol MCX, X is a mountain climber, and not SKX, X is not a skier. So you have to infer the 11th expression from the given 10, and this is done through resolution refutation. Okay, so at this point, let me ask you, was resolution refutation done in your course on logic? Resolution refutation is that. Okay, so then this resolution refutation you're familiar with, but see its application in AI problem solving. This is a problem which falls into a particular category of AI problem. This is called question answering system. So whenever we interact with a chatbot, at every stage, a question answering system is operating. Okay. What is the capital of India? Delhi. So there is a question which is answered. And does it use a predicate calculus? The early incarnations of question answering system made use of some logical representation inside the computer. But now everything is in the form of fill in the blank. Okay, it is token completion using language modeling. So this question is answered from the given facts, and that is done through resolution refutation. So as the name resolution refutation suggests, the proof is by refutation or contradiction. You assume that there is nobody who is a member of the club and meets the description that that somebody is a mountain climber and not skier. So in resolution refutation, what we do is that we negate the structure to be proved. Okay. So now we clean up the predicate calculus expressions. So you have member A, member B, member C, and then every member is either a mountain climber or a skier. Now for all x, member x implies mountain climber x or skier x. This can be written in the form of member x implies MCX or SKX. So this is called universal quantifier dropping. You are allowed to drop the universal quantifier from the expressions. And then you convert implication to not of or and end of right hand side. So this member x implies MCX or SKX is in the form of P implies Q, which is not P or Q. So now it will become not member x or MCX or SKX. Okay. For all x, SKX implies like x no, also can be written as not SKX or like x no. After dropping of universal quantifier and converting implication to not and or. So what we are doing is that we are representing all the pieces of knowledge in clausal form. Okay, these are called clauses. For all x, MCX implies not like x rain, can be written as not MCX or not like x rain. For all x, like AX implies not like BX is written as not like AX or not like BX. For all x, not like AX implies like BX is written as not of like AX, which is like AX or like BX. Like A rain, I don't have to do anything. Like A snow. And the formula that I want to prove, there exists x member x or mountain climber x and not SKX is negated. So you probably know that existential quantifier when negated becomes universal quantifier. And the negation can be taken inside. So this formula is equivalent to for all x, not member x, or not mountain climber x, or not skier x. This is De Morgan. So not of A and B and C is converted to not of A or not of B or not of C. So now all the processing on these formulae have been done, and we are ready to take the next step. The next step is called standardizing the variables apart. And that is important because we are interested in a particular variable through which the answer to the question will be obtained. So standardizing the variable apart means that for every formula, it will have its own variable. So member A, member B, member C, not member X1 or MCX1 or SKX1. See what has become of the statement that every member is either a mountain climber or a skier. So that language sentence has become not member X1 or MC X1 or SK X1. Every skier likes snow. So not SK X2 or like X2 snow. No mountain climber likes rain. Not mountain climber X3 or not like X3 rain. Whatever B likes, A dislikes, and whatever B dislikes, A likes. So not like A X4 or not like B X4. So like and LK are same. LK A X5 or LK B X5. So all expressions you see have their own variables now. Because what will happen is that when we carry out resolution refutation, you probably know that through resolution refutation, the variables get bound, and that's called unification. So through unification, we will obtain the answer. So like A rain, like A snow, and we have the final formula which needs to be proved. Is there a member who is not a mountain climber but a skier? So that is converted to not member X6 or not mountain climber X6 or not skier X6. So we are interested in this variable X6. The answer will come in X6. Okay. So now let us see what happens to this whole set of formula and the knowledge. So we apply resolution refutation. In resolution refutation, there is a search process involved. We always have to choose a pair of clauses which can unify and give rise to a new clause. And that new clause becomes useful in further processing. So let's look at this. So we are trying to replicate resolution refutation or mimic the reasoning that I did some time back. What was the reasoning? A likes whatever B dislikes, and A dislikes whatever B likes. So since A likes snow, let me make use of the knowledge that A dislikes, A likes whatever B dislikes. Okay. So see here, like A snow and not like A X4 or not like B X4 are resolved together, giving rise to the clause not like B snow. Just remember unification from a logic course. Here X4 gets bound to snow. So we get like A snow and not like A snow or not like B snow. X4 has become snow. So not like A snow and like X snow, they cancel each other. This is the resolution. And both the clauses, both the predicates are dropped. And we get not like B snow. So we have been able to infer that B doesn't like snow. Okay, as we did for in our reasoning. B doesn't like snow. Next, we'll have to look for an appropriate clause with which to resolve this. So not like B snow is resolved with not skier X2 or like X2 snow. We are trying to prove that B is not a skier. So we are mimicking the human reasoning, but a machine which doesn't have any other knowledge than only the clauses will have to carry out a search. And that search could sometimes lead to completely dead end. So not like B snow and not SKX2 or like X2 snow. Here X2 gets bound to B. When X2 gets bound to B, we have not like B snow and like B snow. So they cancel each other, giving rise to not SKB by unification. So we have proved that B does not like scare. So far, so good. We seem to be, proceeding in the right path. Then we take the formula which says that every member is either a mountain climber or a skier. So I resolve not SKB with not member X1 or MCX1 or SKX1. Now by unification, X1 becomes B. SKB and not SKB cancel each other, giving rise to not member B or mountain climber B. Okay. Now I'm looking for an appropriate formula to resolve with. So not member B and MCB is resolved with member B. So member B and not member B cancel, giving rise to mountain climber B. So now you might come back and say that now the inferencing is done. You have got your success. You have proved that B is a mountain climber. You have also proved that B is not a skier. So here you can stop and give the answer. But no, resolution refutation as an algorithm has a specific demand for termination, just like A star algorithm. When does A star terminate? A star terminates either by emptying the open list, which is a failure case, or by shifting the goal clause from open list to closed list, which is the success case. Resolution refutation also can terminate only by proving what is called the null clause. Okay, a null clause indicates a contradiction in the system. So we are yet to achieve a contradiction. Let's see. Now this clause of every member is a mountain climber or a skier, this is used again. So this clause is being used twice. Now B gets bound to X6. Remember, X6 is the variable we are interested in. So not member X, not member B, not MCB, SKB, and MCB. So MCB, not MCB cancel each other, giving rise to the resolvent, not member B or SKB. Now, not SKB was already proved in the system. So here I'm making use of a proved clause, not given clauses. So not SKB is taken, resolved with not member B or SKB. SKB and not SKB drop, giving the resolvent as not member B. But B is already asserted to be a member, so not member B and member B get resolved to null clause. It's a contradiction. So this is how the puzzle is solved by resolution refutation. In the lab, you will have to implement this puzzle using Prolog. Okay, you'll have to learn Prolog and solve this puzzle using Prolog. That will be after midsem. Okay, so then you will have a sense of how question answering is done in an AI system. Okay, now several things can be said about the resolution process here. You have to always note that resolution refutation stops with null clause, which shows a contradiction. Now, this contradiction is something we need to understand carefully. What is happening is that if we assert that there is no member in the club who is a mountain climber and not a who is a mountain and not a skier. If we say this is true, then it leads to internal contradiction. Okay, it leads to internal contradiction. The system becomes inconsistent. So proving of null clause is equivalent to proving F. And proving of F, we know is the sign of an inconsistent system. So saying that there is nobody who is a mountain climber and not a skier leads to a contradiction within the system. So this is the heart of resolution refutation. Okay. And in the resolution refutation, you must have understood the efficiency of search depends on choosing the correct pair of clauses. At every stage, we have to choose the correct pair of clauses. What I strongly recommend is to use another path of resolution refutation to arrive at contradiction. Don't start with these two clauses. Okay, try to show a contradiction by taking some other pair of clauses. And that actually happens in a resolution refutation system, a prologue-based system. In a prologue-based system, a considerable machinery is used to make the search efficient, goal-driven. Okay, at every point you strive to choose exactly that pair of clauses which produces contradiction. Okay, so now we would also like to trace the variable we are interested in, which is x6. Okay, because the answer comes out from x6. So indeed, x6 gets bound to B, and we produce the answer as B. Okay, so any question on the resolution refutation you have done before? That's true. When applied to an AI scenario, a practical AI problem, this is how it operates. Now, the importance of standardizing the variables and keeping track of variables. So we did a problem long back. Okay, I believe it was for some airlines company. And we had to implement a prologue-based system which had a simple question answering requirement. And that prologue-based system had something close to 2,000 clauses. Okay, very large practical system, 2,000 clauses. And these 2,000 clauses had maybe something like, 15, 20,000 symbols and operators in the form of or and. Okay, so it was a major exercise. And since the number of clauses was so large, the variables were so large, it was a nightmare to retrieve the answer from the variable of interest. So we had to very, very, carefully and consciously introduce variable for every clause and keep track of that particular variable in which we were interested in. Okay, so unless you do that, it becomes very difficult to debug that system. So, so making use of resolution refutation to solve question answering is one of the high points of artificial intelligence. Of course, these days it is done by making use of huge amount of training data, language model. Okay. This is resolution refutation. Now let me draw your attention to many very important and well-known examples from predicate calculus. So this is a well-known deductive logic formulation. Man is mortal. Now, a key point is to know whether the piece of knowledge is a fact or rule. To convert man is mortal to a predicate calculus expression, will you need an implication or not? So if any of you, any group is taking up this tool to convert natural language sentences to predicate calculus, we'll have to solve this problem. So man is mortal, is it a fact or a rule? It is actually a rule in disguise. What it is saying is that if some entity is a man, that entity must be mortal. So the equivalent expression is for all x, man x implies mortal x. Shakespeare is a man. Is it a fact or a rule? It's a fact. Man, Shakespeare. So now we are going to the building blocks of predicate calculus. To infer Shakespeare is mortal, we have to prove that this predicate mortal Shakespeare. So how do we convert? How do we get our predicates? Okay, so now take the AI view, not formal logic view, AI view. Shakespeare is a man, is giving rise to man Shakespeare. So our ordinary sense of English syntax comes into help here. So in this sentence, Shakespeare is a man. There is a subject part and a predicate part. The subject is Shakespeare. Is a man is the predicate part. So that's why it's called a predicate. And the name predicate calculus comes from this old language-based concept. So you take the predicate part and take the subject as argument of the predicate. Okay. So man is converted to a predicate and Shakespeare is the argument of the predicate. A predicate is a function which evaluates to true or false value of the argument. These two components in a predicate are called predicate and argument. Okay, so this is a single place predicate. It has only one argument. You can have n place predicate where there are n arguments. So man Shakespeare. Shakespeare is mortal. Mortal Shakespeare. Mortal is the predicate. Shakespeare is the argument. How do we prove that Shakespeare is mortal? So predicate calculus actually originated in language. Sentence has two parts, subject and predicate. Grass is green. Here, green is predicate. Is green is predicate. Grass is the argument. Okay. So predicate is a function which goes from the domain D to T, comma F. So we are formalizing the building blocks of predicate calculus. Now, predicate calculus is applicable only for declarative sentences. Sentences which are in the form of statements. Okay, sky is blue, grass is green. Is grass green, which is an interrogative sentence, you cannot give a predicate calculus expression for this. Or an exclamation sentence, oh, grass is green, with exclamation symbol. For this also, there is no predicate calculus expression. Okay, so declarative sentences have subject and predicate. The predicate becomes the predicate. Now you can have a complicated predicate calculus formula depending on how complex the original sentence is. So suppose you have a sentence, grass which is supple is green. Okay, not all grass is green. Grass which is supple is green. So this is converted to this predicate calculus formula for all x, grass x and supple x implies green x. Okay, after looking at the structure of the sentence, it becomes quite clear what the predicate should be. Now, predicate calculus has more expressive power than propositional calculus. This happens because propositional calculus doesn't make use of any variable. Okay, also propositional calculus doesn't make use of any quantification, existential or universal. So suppose you had these statements, 2 is even and is divisible by 2. Proposition number 1. 4 is even and is divisible by 2. Proposition number 2. 6 is even and is divisible by 2. Proposition 3. So if you had to represent the knowledge of what is an even number, then you will need an infinite number of propositions. An infinite number of symbols will be required to represent that knowledge. But see predicate calculus, it makes it so simple and so concise. For all x, integer x and even x implies 2 divides x. Okay. So this one expression captures infinite number of propositions. That's why we say that predicate calculus is much more expressive than propositional calculus. So I hope you really appreciate this point. What would have required infinite amount of memory requires very, very small amount of memory. A few symbols, that's all. For all x, integer x and even x implies 2 divides x. Predicate calculus is also finer than propositional calculus. Okay, and fineness is required to represent intricate knowledge. So suppose you have these statements, grass is green, ball is green, leaf is green. Then you can have a very concise expression, green x, and you can instantiate x with grass, ball, leaf. So it's a succinct description of infinite number of statements, which would need infinite number of properties. So you can also have 3 place predicates. For example, x gives y to z. The verb typically becomes a predicate. We have give x, y, z, which means x gives y to z. So Ram gives a book to Sham. Here x is instantiated to Ram, z is instantiated to Sham, and y to book. Okay. And you can have 4 place predicate. So for example, x gives y to z through w. Give x, y, z, w means x gives y to z through w. So what is good about predicate calculus is that it is a universal knowledge representation scheme. Okay. And AI is extremely knowledge hungry system. Think of sorting. Sorting a set of numbers is not a knowledge hungry system. The only knowledge it needs is the fact of which number is bigger than which number or smaller than which number. It needs the knowledge of a total order for a list of elements. But a system which is doing question answering, understanding of scene, robotic manipulation, navigation of robots, such a system is extremely hungry for knowledge, and representing knowledge in an AI system has been a very important enterprise for AI always. It is universal because let's say if you convert language to predicate calculus, it works for any language. So for example, if we take Hindi. So in Hindi, there is a phenomenon called double causative. Okay. John ने खाना खाया. John ने Jack को खाना खिलाया. Single causative. And then John ने Jack को Jill के द्वारा खाना खिलाया. Okay. So this is double causative. And no problem. Eat John food. Eat John Jack food. And eat John Jack Jill food. No problem. Okay. It all depends on how you interpret the predicates. We will give a formal meaning to interpretation of predicates. Okay. So we have started predicate calculus, which is another pillar of AI. And I hope you remember all the pillars of AI: A star, perceptron, feed-forward network backpropagation, now predicate calculus. Okay. So we are transiting between connectionist AI, neural network-based AI, or data and machine learning-based AI and programming-based AI. So do please take a look at the slides and understand them well. There will be some interesting lab assignments based on predicate calculus. Okay, the class is over.